Hello, I'm Dustin Moss. I'm a researcher in the Flux group at the University of Utah working on Powder, which is an open platform for experimental wireless research that offers users remote access to a variety of compute, networking, and RF resources. Today I'm going to demonstrate how you can experiment with 5G on Powder using OpenAirInterface and our indoor over-the-air lab. OpenAirInterface is an open-source 5G and LTE software stack that provides an end-to-end solution for mobile networking research and experimentation. The Powder Indoor Over-the-Air Lab consists of 4 NI-X310 SDRs with UBX160 daughter cards and 4 Intel NUC compute nodes, each with an NI-B210 SDR and a Quectel COTS 5G UE module. The X310s have fiber connections to near-edge server-class compute nodes, and all of these bare metal resources can be provisioned, configured, and accessed remotely. Powder uses recipes called profiles to define and configure the resources for use in experiments. The profile we're using today automates the deployment and configuration of a variety of hardware resources, along with the OAI 5G core network and gNodeB soft modems. This will be a 5G standalone setup. All of the core network functions will be deployed as Docker containers on a single server class host. The gNodeB soft modem will be deployed on a second server class host with 10 gig fiber connections to the Docker host and the NI-X310 SDR. The 4 NUC compute nodes will be deployed with an image that supports interacting with the COTS UE modules. After instantiating our experiment, we'll log into our compute nodes, start the 5G core network and gNodeB, attach the 5G COTS UE modules to the network, and generate some user plane traffic. You can find links to this profile and the associated Git repository, as well as more information about Powder and OpenAirInterface in the video description. To get started, we'll log into Powder and start an experiment. We'll switch to the OAI Indoor OTA profile. If we click Show Profile, we can see a description of the profile and detailed instructions about how to use it. We'll be stepping through these instructions after we instantiate our experiment, which I'll do now. This will bring us to the parameterization step. We can specify the type of compute nodes we'd like to use for the core network in gNodeB. We can use some advanced parameters that allow for selecting specific commit hashes for the OAI RAN and core network, or a specific disk image for the compute nodes. And finally, we can specify the frequency ranges we'd like to transmit in. The configuration file for the gNodeB in this profile matches the default frequency range here, and you'll need to make a reservation for this range prior to using this profile to instantiate an experiment. It's always a good idea to reserve all of the resources you'll need for a future Powder experiment in order to guarantee their availability at runtime. There is a note in the profile description listing all of the resources you should reserve. In this case, the default set of parameters is just fine, so I'll click Next. That will bring us to the finalize step, where we can provide a name for our experiment and select the Powder project we'd like to use. Choose the Powder project that you used when you made your reservation. Finally, we arrive at the schedule step. Here we can schedule our experiment or select a previously made reservation, which will auto-populate the start and end dates and times. I'll leave these blank, which will start the experiment immediately. This will take a few minutes. After the experiment becomes ready, we'll need to wait for some startup scripts to finish installing and configuring OAI. The startup column in the list view for our experiment will indicate when these scripts have finished. While we're waiting, let's take a look at the topology of our experiment. You can see that this matches the diagram shown earlier. We have compute nodes for our core network host and our gNodeB, along with our X310 SDR and the 4 NUC compute nodes, which each have a COTS 5G UE module attached. Skipping forward a bit here, and looking at the list view, we can see that the startup scripts have finished. Now we'll step through the instructions in the profile. First, let's log into each of the nodes in our experiment. The list view in the web UI shows the SSH commands that we can use to do this. I'll be using a terminal multiplexer called tmux in order to create multiple terminal sessions on each of the nodes, but you can use whatever method you like to accomplish the same thing. Here I've created a single tile in my terminal emulator for each node in our experiment, logged into each node, and started tmux. The top left tile is the core network host. The top right is the gNodeB host, and the bottom 4 are the NUCs with UE modules attached. The first thing we'll do is start up T-Shark on the core network node in order to monitor traffic between the various network functions and the gNodeB. In another session on the same node, we'll start the core network Docker services. This will take several seconds and eventually indicate that the core network is up and healthy. After that, we'll use the same session to monitor the logs for the access management function so we can see our gNodeB connect and our UEs attached to the network. Next, we'll start the gNodeB. As we do this, we'll see some traffic via the T-Shark and AMF logs on the core network node indicate that the gNodeB is connected. Next, we'll bring each of the UE modules online, starting with the one attached to OTA NUC1. In order to do this, we'll first start the Quectel Connection Manager, which handles some of the steps necessary to establish the network connection. Then, in another session on the same NUC, we'll use a tool provided by the profile called Modem Control to bring the UE out of airplane mode. As the UE comes online, it will find the cell provided by the gNodeB and attach as indicated by the T-Shark, AMF, and gNodeB logs. For some reason, the connection manager will not set the IP address it gets via DHCP for the WAN interface associated with the UE module, so we'll do that next. We'll also set a route toward the Docker Bridge network on the core network node via the same interface. Finally, we'll start to ping the OAI external data network service running on the core network node. We should see the ICMP traffic generated at the UE in the T-Shark log. Now we'll follow the same process for the rest of the UEs. You can see that we now have all 4 of the UEs in the lab attached to the network and generating user plane traffic via ping. That's the end of this OAI 5G demonstration using the Powder Indoor Over-the-Air Lab. We hope this will serve as a useful jumping-off point for Powder users. Thanks for watching, and special thanks to the National Science Foundation and the OpenAirInterface community.